All right, so let's talk about some phase changes and the energy required to do them. So start off with a question. A pot of water is boiling. Assuming, normal atmospheric pressure, what's the temperature of the water? And the answer is 100 degrees Celsius, right? Water under normal atmospheric conditions boils at 100 degrees Celsius. So you set the water to boil, and an hour later you come back, it's still boiling. What's the temperature? And so you might be tempted to say that it's above 100 degrees Celsius, but if you stuck a thermometer in there, you would be wrong. It is still 100 degrees Celsius. It doesn't matter how long you boil the water for, assuming the pressure stays the same, it's still going to be 100 degrees Celsius. So the question is, where is the energy going? Right? We're heating this, we're heating it, so we're adding energy into the system. Where is this energy going? Well, it's going into the molecules to break the intermolecular forces and allow them to go from a liquid phase to a gas phase. Same thing this picture is showing right here. Zoom in on this. So you've got ice here, and this temperature, maybe you can't read it too well. It says negative 12 degrees Celsius. And then a little while later, it starts melting. And so water melts at 0 degrees Celsius. So it's melting away. A while later, it's still melting. The temperature is still 0 degrees Celsius. Yet the system is gaining energy. Where's that energy going? It's to break these intermolecular forces. And then finally, when all of the ice has melted, it starts increasing in temperature up to 22.2 degrees Celsius, or whatever room temperature would be. And so let's think about what we're saying here in terms of a diagram. So on the y-axis, we'll put temperature. On the x-axis, we'll put heat added. And so we'll start off with a solid. So we've got a solid down here, and we're going to heat the solid. What's going to happen? Well, the solid's going to increase in temperature as it heats. And then what happens when you heat it enough? Well, the solid is going to start to melt. But just like this ice, once that melting is starting to occur, the temperature is not changing. Even though we're adding heat, the temperature is not changing, because that energy is going to break the intermolecular forces. Only once all of the solid has melted in the liquid will it begin to heat again. So then we have a liquid, and then we can do another phase transition, right? Our boiling pot of water, it's still at 100 degrees Celsius. So even though we're adding heat, temperature is not increasing. And then finally, once all the liquid has been turned into gas, if we keep heating the gas, we can increase the temperature further. And so there's the diagram of that. Here's kind of a math example of this. So the question would be something like, how much heat in kilojoules is required to convert 135 grams of ice at negative 15 degrees Celsius into water vapor, so the gas, at 120 degrees Celsius. And then you're given a bunch of equations, right? Think back to Chem 101. You know Q equals mc delta T. The heat is equal to the mass times the specific heat times the change in temperature. You're given the specific heat of ice is 2.09 joules per gram degree Celsius. The specific heat of water is equal to 4.18 joules per gram degree Celsius. And then the specific heat of steam or water vapor is 1.84 joules per gram degree Celsius. And then you're given delta H of fusion, which is melting, is 6.01 kilojoules per mole. And then the delta H of vaporization is equal to 40.67 kilojoules per mole. Notice that the delta H of vaporization is the highest energy requiring thing because turning things into gases takes quite a bit of energy. So let's think about our phase diagram and where we're starting off at, right? So we're starting off at ice at negative 15 degrees Celsius. Think about when ice melts at 0 degrees Celsius. So in the first component, we're right here. We're heating up our ice. So the first component is heating it up. We're talking about heating something, so we're talking Q equals mc delta T. The mass we were already given is 135 grams. The specific heat we can pull from the C of ice, which is 2.09 joules per gram degree Celsius. And then we multiply by the change in temperature. It's going to go from negative 15 degrees Celsius all the way up to 0 degrees Celsius. That's a change in 15 degrees. So the delta T is 15 degrees Celsius. You'll notice all the units cancel out nicely so that we are left with joules. Notice though that the question tells you to do this in kilojoules. And so I'm just going to divide by 1,000 to change our joules into kilojoules. So what you should end up with here is 4.23 kilojoules. But that's just the heat to go from ice at 0 degrees Celsius or negative 15 degrees Celsius to 0 degrees Celsius, right? Think about what we have to do next. In step 2, we have to melt the ice. And so what we have to use here is our delta H of fusion, right, of melting. Notice the units here are kilojoules per mole, kilojoules per mole. So we have to go from a solid to a liquid, and so we have to change our grams into moles. So we have to take 135 grams of water, and then we want to divide by the molar mass of water, which you can look up is 18.02 grams per mole. The grams cancel out. And then we can do another conversion factor, right? This is 6.01 kilojoules per mole. We have mole up here, so we want mole down here. So we put this 6.01 kilojoules per 1 mole down here. The moles will cancel out, and then we're left with an energy of 45.02 kilojoules. And then you think of step 3 here. Step 3, we have to heat the water from 0 degrees Celsius up to 100 degrees Celsius. So again, we're going to be following our Q equals mc delta T. Make sure you use the C for the specific heat of water. The delta T is going to be 100. The mass, still the 135. So go ahead and do that on your own. I won't show you how to do that. Step 4, we're going to vaporize the water. We're going to vaporize the water. For this previous step, the answer that you should end up with, let's see, is 305 kilojoules. Oops, my bad. No, not this one. 56.4 kilojoules to get it up to 100 degrees Celsius. And then if we think about what step 4 is, we have to vaporize the water. So step 4, you're going to do something very similar to step 2, except you're going to use the specific or the heat of vaporization, not the heat of fusion. So go ahead, plug that through. You should end up getting 305 kilojoules. And then finally, in step 5, we go from 100 degrees Celsius to 120 degrees Celsius. So again, we use our Q equals mc delta T. Make sure you use the heat for the steam, and then the delta T here is just going to be 20 degrees Celsius. So what you should end up getting is 4.97 kilojoules. And then the last thing you want to do is sum up all of these numbers for a final answer of 416 kilojoules, right? That's how much energy it's going to take ice from negative 15 degrees Celsius to water vapor at 120 degrees Celsius. So be comfortable with these phase diagrams, be comfortable with this math component. It's nothing too difficult. It's just a whole lot of steps and pretty tedious, but nothing too difficult.